This lecture we are going to solve a problem related to filtration. So we are going to apply the filtration theory that you learned during the lecture hours. This is slightly a tricky problem. You have to read the problem in order. First you should understand the problem and the statements made in this problem. Only then you can solve the problem. Yeah? It's slightly tricky, but it's easy to solve if you understand the problem. So I'm going to read the problem first. So what we have here. So in the filtration of a sludge, the initial period is affected at a constant rate with the feed pump at a full capacity. So until the pressure difference reaches 400 kilonewtons per meter square, and then the pressure is then maintained at this value for a remainder of the filtration. So and then the constant rate operation requires 900 seconds, and 1/3 of the total filter rate is obtained during this period. First I will read and then I will explain one by one. And then neglecting the resistance of the filter medium, we have to calculate just to follow the green pen on the screen. So neglecting the resistance of the filter medium, so the resistance offered by the filter medium we are going to assume it's negligible. So determine the total filtration time. That's something you need to calculate, and then you have to calculate the total cycle time as well. So we will come back to this, what is cycle time, and then the filtration cycle with so this is the second part of the problem. It is B, the filtration cycle with the existing pump for a maximum daily capacity if the time for removing the cake and reassembling the press is 1200 seconds. So we filter them and then we are going to remove the cake and then reassemble the press, and this time alone is 1200 seconds, and we are not going to wash the cake, so the cake is not washed. So we need this information, 1200 seconds, that's the time that we need for removing the cake and reassembling the press. And then if we know the filtration cycle plus the time required to clean the filtration unit by removing the cake and reassembling the press, that should give the cycle time. Yeah, so that's something we need to calculate. So if we go back to the problem, what it says is like so we are doing some filtration process, and during the initial stage when the pump is operating at full capacity, so we are collecting the filtrate at a constant rate. So once the pressure, so at that time pressure difference can change, but which one is constant is your filtration rate, because your pump is operating at your maximum capacity. But once the pressure reaches 400 kilonewtons per meter squared, and then we are going to do the filtration. So once you start to build some cake, and then we are going to maintain a constant pressure for rest of the filtration. So until you finish the whole filtration process, everything will be performed at the filtration will be performed at a constant pressure. And we have some numbers here. So this constant rate operation requires 900 seconds, and then at the end of the constant rate we collected 1/3 of the total filter rate during this period. So that's the problem, and we need to solve. So before solving the problem I'm going to, maybe I can make some figures that may help you to explain. So what in the problem is what we stated in the problem is, say like we started the filtration process when time t is equal to 0, and then our pump is operating at its maximum capacity until you reach say some time t is equal to t1. So from t equal to 0 to t1 the pump is operating at its maximum capacity, and we are performing the filtration at constant rate. So this is constant rate, and once you reached time t is equal to t1, your delta p reaches 400 kilonewtons per meter square, and from there t equal to t1, so let's say t is equal to t, or this can be t final, until the end of your filtration. We are operating the filtration unit at constant pressure. So and then we are going to, so from T1 we are going to maintain the pressure difference constant, which is around 400 kilonewtons per meter square. So from T equal to T1 to T equal to T, we are going to run everything at a constant pressure, and from time T equal to 0 to T equal to 1, we are going to filter at a constant rate. So these are something that you need to remember. And then if we go back to the problem, we also have some few more numbers. So the constant rate operation requires 900 seconds, which is here, and then at the end of the constant rate filtration, we also have 1/3 of the total filtrate volume. Yeah? So that's the volume at the end of your constant rate operation. So if you want, we can write it, or maybe draw some figures to make it to understand bit more easily. So when time t equal to 0, let's say Vf, volume of filtrate, that should be equal to 0. And then when time reaches t is equal to t1, so that's the constant rate period. Your volume, let's call it V1 for the beginning. It reaches V1, and from V1, and that's V is equal to V1 when time reaches T1. So V is equal to V1, or that's the volume of filtrate that we collected at the end of constant rate filtration. Yeah? So that's what we stated in the problem. So that's how we perform the experiments. So from V1 equal to V1, we are going to from this point we are going to perform the filtration. So once you collected volume of V1, we are going to perform the filtration at constant pressure. Hope I explained clearly. So at the end of your experiment, let's say our final filtrate volume is V. So this part, just follow the pen, that's constant pressure filtration. So just t equal to 0 to T1, volume will be equal to 0, volume of filtrate will be equal to V1, and when T1 to T, your volume of filtrate will be, let's equal to V. And if we go back to the problem again, what I stated here, so the constant rate operation requires 900 seconds, and 1/3 of the total filtrate is obtained during this period. So which means in the problem we know what is T1. T1 is 900 seconds, and then we also have some idea about V1. If the final volume is V, so that's the total volume, or total filtrate volume, and then V1 is equal to 1/3 of the total volume. So V1 equal to 1/3 of the total volume, or the total volume is equal to 3 multiplied by V1. So these are some given parameters. So if you read the problem, I think you know what it says. So what we need to calculate now is the part A of the problem is we need to calculate the total filtration time, and total cycle time. So we have some information about volume of filtrate, and then we are operating the filtration in two different regime, or one at constant rate, another one is at constant delta P, and we already know the time here is 900 seconds, so we need to calculate the time here. So what we can do, so since we know this value 900 seconds, we need to calculate the time required for filtration when you are operating the filtration process, or when you are running the filtration process at constant pressure. Okay, so let's solve this one by one. And before that, let's give few more notation to make our life a bit more easy. So what I'm going to do is, from time, look at the pink lines on the screen. Wherever you see the pink ink, that's the, just focus your eyes on that area. So we have T1 and we have T. So what I'm going to do is, from T1 to T, so that's the time or the period where we are going to operate the filtration process at filtration unit operating. We are going to operate the filtration unit at constant pressure, or delta P is going to be constant, and the time or the total time, filtration time from T1 to T, I'm going to call it as Tp. So that's the total or the time, how to say it. So Tp will be the time from T1 equal to, sorry, from time T equal to T1 to time T equal to T. So that's the, so P means constant pressure, so that's the meaning of that. So Tp means P suffix, the suffix P stands for constant pressure time, something like that. Yeah. So we need to give notations, if not it's very difficult to solve this problem. So what we have here, T equal to 0 to T equal to T1 to T equal to final time T, or if we can write total time, or the total filtration time will be equal to T1 plus Tp. And if you follow this notation here, so Tp will be equal to, or Tp will be equal to T minus T1, so that will be equal to your Tp. So we are just giving notation based on the problem, so just to make our life a bit more easy. Obviously you can solve the problem without assigning this type of notations, but I prefer to go this way. So we know that, okay, before solving the problem, let's try to remember all the filtration theories that you learned in the class. Just to follow the pink lines wherever I'm drawing, focus on that point or that area. So for constant rate filtration, so that's how you define your filtration rate. Vf by T is equal to A squared multiplied by delta P divided by mu. Just, I'm not going to read the formula, so that's your formula for constant rate filtration. So I just expanded it here. So T by Vf will be equal to this part of your equation. Just follow the pink lines. And then for constant pressure filtration, T by Vf is equal to, given by this expression. Yeah. So what is this T by Vf? So this is an expression which relates volume of filtrate to your time. So time and volume of filtrate is connected by this equation. If it's a constant pressure filtration, and if it's constant rate filtration, then time and volume of filtrate that you collect is given by this expression. So if you know the volume of filtrate, then you can calculate the time. If you know the time, then you can calculate the volume of filtrate, provided we know the other parameters like viscosity of the broth, resistance offered by the medium, density, and density of the cake, and so on. So let's go to solve the problem. And since we already know T1 is equal to 900 seconds, now we need to calculate Tp. So how to do that? So we know at constant pressure, so for constant pressure filtration, let's write the equation. T by Vf is equal to alpha rho 0 by mu 2a square delta P volume of filtrate. Okay, so we need to calculate this time factor, and we know that we are operating the filtration unit at constant pressure, yeah. And so T is equal to Tp. So T is equal to Tp, which is equal to T minus T1. So so Tp will be equal to, so T is what? T So just to rewrite this equation here, T is equal to alpha rho 0 mu divided by 2a square delta p multiplied by Vf into Vf. So therefore T will be equal to alpha rho 0 mu by 2a square delta p into Vf square. So this is the time, filtration time, if you operate the filtration unit at a constant pressure. Okay, so we know that Tp is equal to T minus T1. So and we know when time t equal to T, the volume that we collect, Vf is equal to V. When time t equal to T1, the volume of filtrate is equal to V1. Yeah? So we have this information, so let's calculate Tp. So Tp will be equal to alpha rho mu divided by 2a square delta p multiplied by V V square minus, when T for T1 will be, just use this formula which is here. You have to calculate T1, you have to calculate T. So for T1 will be equal to, say, alpha rho square mu divided by 2a square delta p multiplied by V1 square. So all I did is I applied the theory, constant pressure filtration theory. So take the common factor, alpha rho mu 2a square delta p V square minus V1 square. So this is not bad. So what I am going to do is, I am going to call this a constant. I'm going to call this a constant. So Tp will be equal to, okay, don't call anything. So let's leave it like that. Alpha rho mu 2a square delta p V square minus V1 square. So let's have like that. So to get your Tp value, to get your Tp value, you need to know what's your V, you need to know what's your V1. So only then you can get your Tp value. And you also need to know the value of these constants. So at the moment we don't know what is alpha, what is rho 0, what is mu, what is a square. We have some idea what's the delta p. So we need to know this the value for these constants. So how to get that? To get that, you need to go back to your problem. We already have some information, like if you go back to here, I showed some diagram. When t equal to 0 to t equal to t1, t1 is 900 seconds. So we know the time, and we know the, from there we can get some relationship between time versus volume. So let's do that. So let's, for the constant rate filtration, this is something that we are going to, so we are operating the filtration unit at constant rate only during the early stage of your filtration process. That's roughly around 900 seconds. So for the constant rate filtration, just write the theory which you know. T is equal to Vf, T divided by Vf is equal to mu alpha rho 0 Vf divided by a square delta p, or T is equal to mu alpha rho 0 Vf square divided by a square delta p. So this is for constant rate filtration. and we know when t is equal to t1, which is equal to 900 seconds, this will be equal to mu alpha rho 0 a square delta p multiplied by v1 square, because we know that when t equal to t1, the volume that we collect, volume of filtrate that we collected, is equal to v1. Yeah. So how to rewrite this expression? So mu alpha rho 0 divided by a square delta p, that's equal to 900 divided by v1 square. So we have some value for this constant, mu alpha rho suffix 0 divided by a square delta p. So this is something that we have at the moment. So let's call this as equation 2, and let's call this as equation 1. And then, so now substitute 2 in, so we have the value for mu, we have the value for here, mu alpha rho 0 divided by a square delta p, that's equal to 900 divided by v1 square. So substitute 2 in 1. So to get TP will be equal to 900 divided by v1 square multiplied by 1 by 2, that's equal to, sorry, multiplied by v square minus v1 square. Yeah? And if you, earlier I stated that the relationship between v and v1, that's we know that v is equal to 3 times v1. This is something which is given in the problem. So substitute this value here in that above equation. So which means your TP will be equal to 900 divided by v1 square, so 2v1 square multiplied by 3v1 square minus v1 square. So TP will be equal to 900 divided by 2v1 square multiplied by 2v1 square. So both get cancelled. So TP will be equal to 900 seconds. So the constant filtration time, that's equal to 900 seconds. Okay, I think we almost solved the first part of the problem. So the total filtration time, will be the time that we operated our filtration unit at constant rate, and then the time that we operated our filtration unit at constant pressure. So total filtration time, that will be equal to T1 plus TP. So we know T1 is already 900 seconds plus TP is 900 seconds. So that will be equal to 1800 seconds. So that's the total filtration time. And then we need to calculate the cycle time. So total cycle time is the filtration time plus the time that you require to remove the cake and then set the filtration unit ready for the next job. So total filtration time will be equal to 1800 time plus the I forgot the number. So we can call, okay, what's that number? 900 seconds, blah blah blah, it's 1000. Okay, the time for removing the cake and reassembling the press is 1200 seconds. So let's call this as downtime, TD. So TD is equal to 1800 plus 1200 seconds, that's equal to 3000 seconds. So that's the total cycle time. Okay, so this is not bad. And then I think we solved the part A of the problem. So part B is okay, let's put a box here. Total cycle time is 3000 seconds. Filtration. And then let's go to part B. So what I asked in part B is the filtration cycle with existing pump for a maximum daily capacity. If the time for removing the cake, okay, again the time for removing the cake and reassembling the press is the 1200 seconds. But what I ask you to calculate is what will be the time required for the filtration if you are operating the or if the rate of filtration or the total rate of filtration is maximum. Yeah, in that case what will be the time required for filtration, and then what will be the cycle time for that case. So we need to find the filtration time, provided the condition is the filtration rate is set to maximum. Yeah? And again the filtration process goes through a period of constant pressure and then constant rate. So you have some constant rate followed by constant pressure. Irrespective of the way we operate, we need to know what will be the filtration time if the filtration rate is set to maximum. Okay, at the end of the day the rate of filtration is set to maximum. Whatever the volume of filtration filtrate that you collected in that time per unit time, that value should be maximum. If that value should be maximum, what should be the time of filtration? Okay, that's something you need to calculate. It's not a big deal, it's really easy. So for constant rate period, again write the formula that we already know. Just turn the page. So let's solve B. So again we know for constant rate period, this is a very long problem, you need to practice in home. T1 is equal to alpha mu V. In the exam I will give the formulas for the filtration theory, but you should know how to use those theory, that's really important. So you have a constant rate period T1, and so that's the formula we used already. So I'm going to call this parameter as constant. This everything that you see here, that's a constant. Alpha is a constant, mu is a constant. This is rho. Rho is a constant divided by a square multiplied by delta p. Everything is constant and multiplied by vf square. Okay, so let's call this as k multiplied by vf square. So T1 is equal to this is equal to k into V1 square. We already know that when time t equal to T1, the volume of filtrate is equal to V1. So T1 at the end of the day is equal to k multiplied by V1 raised to the power 2. And then for constant delta P, we know that Tp is equal to T minus T1, and we already derived this one in the previous page. Alpha rho mu divided by 2a square delta p. I showed you this will be equal to v square minus v1 square. So this is equal to, so this part is equal to k, so this is equal to k divided by 2 multiplied by v square minus v1 square, so Tp. So that's the time, total time that we operate our filtration unit at constant pressure, that's equal to Tp. And we know that the total filtration time T is equal to T1 plus Tp, or this is equal to T1 plus T minus T1. This is something I showed you already just a moment ago. So T will be, so substitute the equation here. What's T, and what's T1? So let's substitute. T is equal to, so at the moment we are dealing with constant pressure. We're operating the filtration unit at constant pressure. So T is equal to T1 plus T minus T1 or maybe just T is equal to T1 plus Tp. And if we go back to this page here, let me check a second. Okay, let's give this some equation number 3. So we know T equal to, and okay, and let's call this equation 3 and let's call this equation 4. So we know that T is equal to T1 plus Tp. Let's call this equation 5. So substitute, sorry for going very slow, but this is a very tough problem. Substitute equation 3 and 4 in equation 5. So we get T is equal to kV1 square plus k by 2 v square minus v1 square. So expand the equation, kV1 square plus k by 2 v square minus kV1 square by 2, that's T. I'm going to take the common factor like LCM, so divide by 2. So 2 kV1 square plus kV square minus kV1 square. So T will be equal to kV1 square plus kV square by 2. Okay, everything looks good until this point. kV1 squared T is equal to kV1. Okay, so for the entire filtration process, let's say you start from T equal to 0 and then you end up at the final T is equal to T. Obviously somewhere at this point you have T equal to T1, so this is your constant rate zone, constant, and dV by dt, and then here delta P is constant. So from T equal to 0 to T equal to T, if you want to define a total filtration rate, it will be equal to the amount of filtrate that you collected, Vf by T. So we know the total volume that we are going to collect is V divided by T. So that should give the total filtration rate. So you have to think a bit before we solve this type of problem. Okay. So the total filtration rate, will be equal to V divided by T, and just imagine you have some downtime. So the total filtration rate will be equal to, if we have a downtime, I think in this case is equal to 1200 seconds. Let's say tau downtime is indicated by the notation TD. Then the total filtration time equal to V divided by T plus TD. Once you solve this problem, you will understand what we are solving at the moment. This is very tricky problem, and sorry for going very slow. So V divided by T plus TD. Oh, what is this? So V divided by T plus TD. So we already know what. So we know that T is equal to just this value here. So I'm going to call this as equation A. We already solved for T, so we know T is equal to kV1 square plus kV square by 2. So substitute this value here. So we know V by T plus TD, that's equal to V divided by. So this part you have to do in the exam. If I ask some problem, something like this, I will give only the value of the I will give only the formula of the filtration theory. You have to come up with this calculation. You have to do these calculations. So that's why you have to practice in home. So V by T plus TD. So T is equal to kV1 square plus kV square divided by 2 plus TD. So you can expand this equation. V divided by kV1 square plus kV square plus 2D, and then you will have 2 on the numerator. So V by T plus TD. So this is nothing but your total filtration rate. So I will tell why we are calculating all these things. So this total filtration rate should be maximum. Okay. From time t equal to 0 to end of your filtration, my filtration rate will be defined by this equation. Yeah? So let's try to simplify this equation. How to simplify it? So V by T. So let's call this as TF. So TF means the total filtration time. Okay. So that's equal to 2V divided by kV1 square plus kV square plus 2 TD. So that's the total filtration rate. So for the rate to be maximum, if you are operating the filtration rate to its maximum, then what will be the time required for filtration? That's something we need to calculate. So how to calculate that? So if you want to, I don't know whether you know this, you are in the final year of chemical engineering. So if you have any function like that, say like this is y, this is x. So if you need to find the maximum point, which is here, I think I already taught you these things in the when we are trying to derive the productivity in a continuous stir tank fermenter. So if you have anything something like here, if you want to know where the maximum point occurs, all we need to do is we need to differentiate dy by dx and set the value to max 0. So what it says is like there is something changing with y is changing with x, y is changing with x throughout this line, and then it reaches some point on the top, and then again it will change with respect to x. So at that particular point something is going to be constant, and if you differentiate a constant with respect to something, that should be equal to 0. So if you differentiate the the change in y with respect to x and set it to 0. That should give the point at maximum. Yeah, so that's what we are going to do. So we need to calculate the time total time of filtration when the rate of filtration is set to be maximum, is set to maximum. Yes, set, not set, set to maximum. So how to do that? So that will happen when the change in rate with respect to the volume of filtrate that we collect is equal to 0. Yeah. So what I'm going to do is I'm going to differentiate V divided by TF divided by with respect to change in volume, the change in rate with respect to change in volume. If this value is constant, if we set this value equal to 0, that should allow you to calculate the time total filtration time for the condition or when we set or when we are performing the filtration whose filtration rate is set to maximum. Yeah, my god, it's very difficult to explain this. Huh? So how to do that? So this is the time that we are going to calculate when our filtration rate is set to maximum. So to do that, all you need to do is you have to, let's call this as equation 6. We need to differentiate equation 6 with respect to volume. So we have to differentiate the whole equation to kv1 square plus kv square plus 2d td with respect to volume. So for convenience, what I'm going to do is I'm going to call v is equal to x, kv1 square is equal to a, and then 2 multiplied by td is equal to c, and then just k is equal to b. So which means you can write this something like here 2, so differentiate of 2x divided by a plus bx square plus c. So if you differentiate this, you will get 2 minus bx square. I don't want to perform the full differential calculus, the calculation part here. It will take another 40 minutes, so I don't want to do that. Bx square plus c the whole square. In the exam I will give this formula if you have this type of question, so don't worry. So now substitute all these values back into this expression. So you will get equal to 2 minus kv square plus kv1 square plus 2 td divided by kv1 square plus kv square plus 2 td, that's equal to 0. So we are setting the change in rate with respect to change in volume, filtrate volume, to 0. So you can write 2 minus kv square plus kv1 square plus 2 td. So this one goes to the right hand side, that's equal to 0. So just expand the expression 2 kv square plus 2 kv1 square 2 into 2 plus 4 td, that's equal to 0. So we need to so from there we can get the td value. So 4 td, that's equal to 2 kv square minus 2 kv1 square. So td will be equal to 1/2 kv square minus kv1 square. So let's put a box. Let's call this what's called equation 7. So equation 7, and if you go back to the very beginning of our problem, somewhere we calculated what's the TP. So what we have here, so we know already what is T1, we know what is TD. So T1 is 900 seconds, TD is 1200 seconds, and what we need to calculate is TP. TP for the conditions, the total rate, the rate of filtration is set to maximum. Yeah? So how to get that? TD. We know TD is equal to T minus T1 no, not TD is equal to T minus T1, TP. So I'm trying to, okay, let's get this one. TP is equal to, no, this is much easier to solve. TD is equal to half, I'm just reading the equation 7, which is here. TD is equal to half of kV square minus kV1 square, and then from equation oh my god, from equation 4, sorry, equation 4 we have TP is equal to K by 2 V square minus V1 square. So this is your equation 4, which you already solved. So if we compare equation 7 with equation 4, you will see that TD is equal to TP. Both are same. So TD is equal to TP for the condition change in rate with respect to V is equal to is maximum, is at maximum. The total filtration rate is at maximum. So in that case TD is equal to T minus T1. This is something that we know, because we already know TP is equal to T minus T1. So I just substitute in this expression. So that should give TD is equal to T minus T1. So we know TD is equal to 1200. So we need to calculate the time. That's the time at the end of filtration. So that's equal minus T1 is 900. So T will be equal to 2100 seconds. So that's the time required if the total filtration rate is at maximum. Yeah. And now we can calculate the total cycle time. So this is the part B of your problem. Yeah. Total cycle time will be just the filtration time plus your TD, that will be equal to 2100 plus 1200, that should be equal to 3300 seconds. So cycle time. I think that's all. We solved the problem. I'm going to upload this in YouTube, and then probably I will try to solve one more problem in filtration, maybe a bit more easier problem. So obviously I took a lot of time for this one problem, because this is very difficult to do and also to understand. So probably in the next semester you are going to do some experiment, something similar to this problem. You will do some constant rate, and then suddenly you will operate your filtration unit at constant pressure, and then you are going to collect some data, and then you will practically redo the calculation using this video. Yeah. So try to solve it yourself. Watch the video one time and then solve it in home without looking the video. So thanks for listening.